Hello there, and welcome to IQT's The Post-Quantum Dragon podcast. My name is Brian Siegelwax, and this podcast is probably not as quantum safe as it should be. My guest this episode is Eric Hay, Senior Vice President of Field Engineering at Quantum XChange. Thank you for joining me. Welcome to the show.
Thank you for having me.
Okay, my understanding is that instead of simply generating any old private keys, that FIOTX generates one-use-only private keys. Since the implication is that we currently reuse private keys, why are single-use keys optimal and not, for argument's sake, overkill, which would seem to be the counter-argument?
Yeah, so that's a great question. I think there's a couple distinctions to be made. The keys that we're talking about are typically used to protect data in motion. So data in transit between point A and point B, where I need to create like an encrypted tunnel. And for those situations, the challenge is if I have a static key, like a pre-shared key at both ends, at some point I have to rotate it because there's a possibility or probability, some would say, that you can perform some cryptographic analysis on the traffic and then derive that key. And of course, then you worry about somebody stealing it like an insider threat, right? So you want to rotate it. The challenge has always been that it's hard to rotate those because you have to take the network down, you have to get somebody out there to do it. So there's a cost effort. And so what our focus is on is taking that process and automating it and replacing either the manual loading of those pre-shared keys, or the other way we get those keys to both sides, those shared keys, they're symmetric keys, is we use certificates, right? We use public key encryption like RSA, Diffie-Hellman, ECC is the underlying algorithm. And the challenge there is that that's going to be broken by quantum computers. And so even though I don't have a quantum computer today, and we don't think anyone else does, but we don't know, I can harvest data today and copy it off of an encrypted network and then go back in the future and decrypt it and see what was said, right? So that's the threat today. And so the challenge there is how do I fix that? And the way we would say to fix it is to generate these keys and deliver them to the endpoint so that the key is never negotiated between the two endpoints directly, and that buys you a lot of extra security, right? Because if you think about it, if I can copy the data and the keys today off of any network doing, public key encryption, and then I can decrypt it in the future, if I can take the key out of that conversation, then I can copy all I want today, but I'll never be able to decrypt it in the future because the key that I need to get at isn't there, if that makes sense, right? So you're really trying to separate key generation and distribution from the data network or from being physically installed permanently on the endpoints, which is a bad cyber hygiene.
That might compromise my later questions, but I'll just roll with it and see
Keep
if I
going.
can adjust them on the fly. Okay, when we delete files on our computers, we can retrieve them. We can even overwrite files and still retrieve them. So how do you ensure permanent deletion of used private keys?
Yeah, so that's a great question. So I think typically the way we've thought about private keys, again, when we're thinking about on the endpoint, so let's just take like two routers that are communicating with each other, because that's just a simple use case. And I've got private keys installed on there. They're my public-private key pairs or my pre-shared keys. They have to be written to the device so when it reboots, it can get a new key, and that's the challenge. How do I know that it's been deleted? So what we're really talking about is only ever having these keys in memory. And because you can dynamically update them, I don't have to have a state where the two endpoints must be able to start from cold and have the same key. They can start from cold and request a new key and use that. So you never have to write it anywhere. And if you don't have to write it, you have a pretty high level of confidence that if it's in memory only, that it's not going to be retrievable. And as far as our key delivery, we have a FIPS validated key zeroization process that demonstrates that we zeroize the key before it's actually removed from memory, so that any pointer or residual pointer will not point to actual any data. So that's a process that is mandated by the U.S. NIST FIPS validation process.
Okay, this next question is the one that I think is newly stupid, but I'm going to ask it anyway. But I think you already answered it. But what it was going to be, if a FiOTX box is communicating with another FiOTX box, that sounds like a vulnerability. How is that communication secured? But it sounded like you said pre-shared keys. So how does that work? They're not communicating, they are
Yeah.
communicating?
Yep. No, that's a great question. And so the two FiOTXs are communicating. So let's take again our router, two routers. I've got Alice and Bob router, and Alice and Bob router want to communicate. So instead of negotiating the key directly over the data plane, what they're going to do is they're going to talk to their key provider, which is FiOTX. And that key provider is then going to initiate a key generation at both locations. So the way that happens is when the Alice router makes a request, she says, hey, I want a 256-bit AES key, symmetric key, and I need a copy to go to Bob, right? Typically, that's been vulnerable and will be vulnerable to quantum computing. What we're doing is now when that request is made, the FiOTX dynamically generates, and you'll hear in memory a lot because we don't like to write anything to disk. It dynamically generates in memory only a key pair for a post-quantum algorithm, or more than one, because you can do more than one. And so it generates these key pairs, and then it sends the public keys over to Bob's key provider. Now, that network path could be in the clear because these are post-quantum pre-shared, post-quantum public keys. And so in theory, they're safe, although we do encrypt that tunnel as well to make it harder for the attacker. But now Bob's key provider takes those, generates a session key, and an encrypted copy of that session key, which goes back. And that can only be decrypted by the owner of the private keys, the private key pair for the algorithm, right? So now Alice's key provider gets that back. It can decrypt it, and now I have a session key at both sides that's only known to the two key providers when it's handed off to the routers, to Alice and Bob, and then they use that to create their data session. And so the impact here is that we've broken the man in the middle, harvest now, decrypt later between Alice and Bob. Because if I'm an attacker, I know that Alice has to talk to Bob to exchange data. I can see the beginning of that conversation and I can start copying. And that's the key negotiation and all the data that key protects. Once you put FiOTX in place, an attacker can see that initiation and they can start copying, but they're never going to actually get the key because it's not in band with the data, right? It's out of band of the data. And so that gives you a really high degree of protection. And then, of course, with this solution, you can rotate those keys very frequently, which also gives you just better cyber hygiene and protection against many things like insider threat.
I think I actually understand that. And let's see. Excuse me. Quote, we are not really protected if we just change the algorithm, unquote. Ironically, I think that was your quote. I think that was you.
It probably is. I may have stolen it from someone else, though, so I don't want to take credit for it.
Well, I think I got that from you, though. But so anyway, so we're saying migrate to PQC, migrate to PQC, and it sounds like you're saying that using post-quantum cryptographic protocols still leaves us vulnerable because of the network architecture. So we're only quantum safe, but we're not safe.
Well, you're only quantum safe as long as you can assume that the algorithm isn't broken. So if I have a connection between Alice and Bob, whether it's an application or routers, whatever, and I change the algorithm from RSA to MLChem, which is the new NIST approved algorithm, and I change it from RSA to MLChem, and I keep the rest of the architecture the same, basically what I'm doing is I'm hoping that the algorithm doesn't break. Because remember, this is a man in the middle attack. So I copy the data, now protected with this post quantum algorithm, right? That's allegedly quantum safe. And I copy that. And in the future, if it turns out there's a weakness in that algorithm where it can be broken, I can go back and replay that data and see what happened, right? I can reread it. And so it's a little bit of a hope the algorithm doesn't break strategy because we're still enabling the same architecture where the key and the data go directly between Alice and Bob. And so if we want to fix that, we have to get rid of that architecture. And it's important to understand the genesis of that architecture. When Diffie-Hellman was created in 1976, so that's 50 years ago this October, and RSA in 77, there was no internet. There was no IP addressing and routing. You didn't have networks the way we know them today. You had point to point communications. And so back then, you had to negotiate the key and the data over the exact same physical network, the exact same logical session. And so the problem is that architecture just stuck with us. Why? Because it worked. And so we've kept it. But now the reality is we don't have to assume there's only one connection between any 2 points, right? Your phone has multiple connections to Netflix and Google and Facebook, and you're talking to multiple things over multiple networks. You've also got a wireless and a cellular network. So you've actually got two physical networks. There's literally no reason to exchange keys over the exact same network and session that we transfer the data over. That it's a bad idea. And so if we can change that, we can break that man in the middle architecture by taking the keys out of the data plane. And that is really why you want to do that because the migration isn't enough. And in fact, people may not be aware of this, but two of these quantum safe algorithms that were being validated by NIST and were in what we call the finalist round were Rainbow, which is a digital signature, and Psych, super singular isogeny. And Rainbow and Psych were broken not with a quantum computer. They were broken by with two different people with basically standard commercial, off the shelf machines. I think one was just a laptop in a matter of a few hours or maybe a day or two. So that's without a supercomputer. And it was done because they realized a weakness in the algorithm. And so I guess our point is we're coming into a new era with quantum and AI coming together, and we don't know what's going to happen. We shouldn't assume that the algorithm is just going to be safe forever. And if we can't assume that, then we should maybe make a change to the architecture so that we're not totally dependent on the security of the algorithm to protect our data. Because I don't think we have that luxury anymore, to be honest.
I'm glad you mentioned 50 years ago, because that's actually my last question. So, but you just kind of answered it. Well, I guess the
Well,
nature of the question was, oh, sorry, go ahead.
no, go ahead. No, go ahead.
Like what took 50 years? So using the same channel as a vulnerability, it was 50 years ago. So what took so long, or why hasn't this been resolved already?
Well, I think it's because standards are very difficult to change if they're working. So, we had the original Diffie-Hellman key exchange and RSA. We had protocols like TLS, which is from 1999. So that's, 27 years ago. It has been around for a while now. And basically they worked. And so we didn't see a need to change them. And there was always this feeling that it was safer to negotiate a key directly between Alice and Bob. And well, I've already got this connection here, so let's use that. And it was really a matter of convenience. And we see this all the time, right? We see it with, whether it's, our wireless going from, 2G to 3G to 4G to 5G. There's a lot of primitives in the authentication and security components of those networks that we've just kept for backwards compatibility and because the standard is there. And we really, if we'd done it right, we probably would have thought about doing it differently, but we didn't. And that's a problem in security generally, is that if it's working and there's some risk to changing it in terms of interoperability, then we weigh the cost of the security versus the interoperability, and very often interoperability wins. And so what you get is, hey, this has been working for 50 years, let's keep doing it this way, right? Or we'll make some minor tweaks to it. And so that's a challenge. I think what we're starting to see, though, just so you know, is that while we've been doing this sort of key delivery for 50 years the same way, we've been doing some other things for not quite as long. but that are also going to have to change. And one of those is our current network infrastructure, with IP networking is and networking in general is we have a basically standards across the internet and in organizations where you have the frame size of the network. The size of a network packet for interoperability is 1500 MTU, so it's 1500 bytes basically, and that works great. And some places they can enlarge the packets for certain types of data, but generally speaking, on the internet, you're going to see 1500 bytes. Why does that matter? Well, because one of the things that we're starting to run into is with these new algorithms, the public key that needs to be delivered between Alice and Bob, these PQC public keys, is bigger than that network packet size. So what does that mean? It means when I try to stuff the key in the envelope, it doesn't fit, and I have to cut part of it off and put it in a second envelope. And that envelope's not full, it's a fragmented packet. And so now I have issues where on my 1500 MTU network, because I can't fit the keys in, I have these multiple pieces that I got to get assembled the right way on the other side and traversing across the internet. Some systems go, it's a fragment, we don't want it, tosses it out. And so there's now a challenge of trying to get these, keys to work on this legacy network, packet size. And so we're jumping through hoops. We've got different RFCs to try to deal with this and what's called hybrid key exchanges. And again, the only reason we're doing it is because we've always done it that way. We've had 1500 MTU for years. It's going to be too hard to change. Well, it might be, but maybe we ought to think about it. And maybe we ought to think about if the handshake protocols we use and the 1500 MTU together conflict, we've got to change one or the other. And we're not really doing that, I don't think, in a great way. And I think that's just human nature. It's always worked this way. It's too hard to change. Oh, we got all these systems out there that can't be upgraded. Let's find some, clever workarounds that are sort of band-aids. And that's a challenge in the cybersecurity industry writ large, right? Is that you have to come up with compromises that sometimes aren't really the best solution from a security perspective, but they guarantee interoperability and more widespread deployment. And so you have to weigh those against each other.
So you bypass that packet issue because the keys don't transit at all.
Well, we're very clever. So we've been working with NIST and with these algorithms since 2000, really since 2017. And so we saw this problem coming a long time ago, and built some mechanisms to handle it that will work on any network infrastructure, because that was really the goal, without having to have crazy hybrid key exchanges and multiple requests and things like that. You had to do some work to make it happen, but we've done it. And it's one of the things that to be honest, it sets us apart is we can do any public key size. So MLChem 1024, HQC 128 is a new one from NIST. That's even bigger, 2200 bytes. Bike L3 and L5 are bigger. We can do classic McAleese with a 262,000 byte key on any network infrastructure and feed keys to any hardware. So that's something that sets us apart, but we work really hard on it. And it is a hard problem to solve. But it can be done. It just took a lot of thinking outside the box, right? And deciding that you didn't care about legacy architectures and you would figure out a way to make it work the right way. And that's what we wanted to do. We wanted to have future proof. In fact, the sad thing is that I mentioned classic McAleese. It's probably the most peer-reviewed post-quantum algorithm because it's been around the longest. And it has the largest keys, which means it's the least deployable. So then you get back to that, hey, it's really secure. Why don't we deploy it? Well, because it's hard, right? So we've made that possible. And it's not even possible to deploy that with some of these new post-quantum RFCs like 9370 for key exchange. That won't handle public keys greater than, I think, 64K. And I'm old enough to remember when we thought, 640K was enough memory on a computer. Not
I
true
remember that
anymore,
too.
right? So when we put these artificial boundaries up, we go, oh, that'll be enough. We'll never have to go beyond that. Let's set that as the bar. We really should be thinking, hey, how big could this get? How large do we need to think? And let's build something that can accommodate that. And it's not easy, right? It's not easy. But if you do that, you buy yourself a lot of flexibility in the future. So we're hoping that what we've done here will sort of bear fruit in that regard.
Makes sense. And with that, I'm all out of questions, so the floor is yours to say anything else you'd like to say.
I'd say if anybody's looking at post-quantum migration, you're probably going through the NIST work streams. Again, we work a lot with NIST, and so discover, where's my crypto, prioritize the applications and devices, endpoints you need to do first, deploy, manage, monitor, rinse, repeat. You're going to do that for a long time. So I think that what I would say is when you're going through that process, you can probably save a lot of time if you think about where your data travels, because this is a transport security problem, and do the wire, and therefore get all the data in that wire. So if I have headquarters to data center and that has all my customer information, my PII, PHI data, whatever, and that's 90% of it, if I do that and make that network quantum safe, think about it from the network level, I don't have to do all those apps right away, right? So that's sort of a way to think about streamlining the effort by tacking the biggest, fattest pipes with the data first. So I would say that's the one thing. And the second thing is we should expect that when quantum and AI are as they're maturing and as they come into working together and people are using them to work together, we should see the pace of change relative to cryptography increase. And that means you'll probably have to do this migration more than once in the next very few years, meaning you'll deploy ML Chem. NIST will come out and say, hey, that may get broken in 6 months based on some projections, or it's already been broken. You'll have to change to something else, and then you'll have to do that again. And we just don't know at this point because Moore's law has guided us for all these decades of doubling every 18 and 24 months. Now you have these brand new compute technologies where it's not a bigger engine in a car that's going faster, which is kind of how we've been doing it. It's a rocket ship that's leaving the atmosphere, right? So it's moving in different dimensions, and that really is going to change the way we have to react to changes or breaks in cryptography. So it's really time for people to start thinking about managing their cryptography a little more than we've never really done it. So to do it in ways we've never done before.
Sounds good to me. Well, thank you again for being my guest on IQT's The Post-Quantum Dragon podcast. And thank you to everyone who's still listening. As always, I invite you to stick around for the outro music. It's called Dungeons and Dragons. Enjoy.